Hello everyone. In this video, we shall discuss Riemann-Stieltje integrability of one more special function, which is a monotonic function. So, statement: if f is a monotonic function on a closed interval a comma b, and alpha is a monotonically increasing continuous function on closed interval a comma b, then f is Riemann-Stieltje integrable on closed interval a comma b. So, in general, to talk about Riemann-Stieltje integrability of a function f, so the necessary condition is f has to be bounded first of all, and along with that we need a monotonically increasing function alpha. So if f is bounded and alpha is any monotonically increasing function, then we can talk about Riemann-Stieltje integrability of f. Just we can talk about it, but f need not be Riemann-Stieltje integrable always. Now, in particular, so if you want to discuss about Riemann-Stieltje integrability of monotonic functions, so recall monotonic functions means a function which is either monotonically increasing or monotonically decreasing. That means as the domain points increase, the function values also gradually increase. So such a function is called monotonically increasing, or if the function values gradually decrease as that of the points increase, then it is called monotonically decreasing function. If f is any one of these two types, either monotonically increasing or monotonically decreasing, then it is called monotonic function. So if we have a monotonic function f, and along with that f is a monotonically increasing continuous function, then f will be obviously Riemann-Stieltje integrable. So a monotonic function f will be Riemann-Stieltje integrable if you take that along with the monotonically increasing continuous function. So in general, alpha need not be continuous. So in general, to talk about Riemann-Stieltje integrability, alpha should be just monotonically increasing function. So in addition to that, if alpha is continuous, then any monotonic function will be Riemann-Stieltje integrable. So this is what the theorem says. So if the assumption or the hypothesis is here, f is a monotonic function and alpha is a monotonically increasing function. So with this hypothesis, we have to prove that f is Riemann-Stieltje integrable on the closed interval a comma b. So we shall start the proof. So first of all, note that f is monotonic on closed interval a comma b. So which implies f is either monotonically increasing or monotonically decreasing. So f is monotonically increasing if f of x1 is less than or equal to f of x2 for any domain points x1 and x2 with x1 less than or equal to x2. That means x1 less than or equal to x2 implies f of x1 is less than or equal to f of x2. So this shows that f is monotonically increasing. So the opposite of it is monotonically decreasing. That is, for x1 and x2 with x1 less than or equal to x2, if f of x1 is greater than or equal to f of x2, then it is called monotonically decreasing function. Okay, so this is the first point. Next, now we have to prove f is Riemann-Stieltje integrable on closed interval a comma b. So to prove this, we shall use the Riemann criterion for integrability. By Riemann criterion for integrability, to show that f is Riemann-Stieltje integrable, it's sufficient to show that for a given epsilon, there exists a partition P of closed interval a comma b such that u p f alpha minus L p f alpha is less than epsilon. So this is what we have to prove to show that f is Riemann-Stieltje integrable, right? So start with an epsilon, let epsilon greater than 0 be given. Now we shall construct a partition, right? What we have to do here, for a given epsilon, we have to show the existence of a partition P with this property, right? So now, given an epsilon, now we shall construct a partition. Okay, so let epsilon greater than 0 be given. Now for any positive integer n, so define x naught to be the first point a of the closed interval a comma b, and xn to be the last point of the closed interval b, and define h to be alpha of b minus alpha of a by n, where n is any positive integer. For any positive integer n, define h to be alpha of b minus alpha of a by n, as B is greater than or equal to A, alpha of B will be greater than or equal to alpha of A, as alpha is monotonically increasing. So as alpha of B is greater than or equal to alpha of A, the difference alpha of B minus alpha of A will be non-negative. So a non-negative number by positive number is always non-negative. So H is non-negative. Okay, now consider this inequality. So alpha of A is nothing but x naught. So alpha of x naught is less than or equal to alpha of x naught plus h. So as we are adding a non-negative quantity to alpha of x naught, so this sum will be obviously greater than or equal to alpha of x naught. And this quantity will be obviously less than alpha of B. This is because, so alpha of x naught plus h. So n is any positive integer, so it will be greater than or equal to 1. So here 1 times h is there, alpha of x naught plus h is there. So consider it has 1 times h. So 1 is less than or equal to n. So alpha of x naught plus h will be less than or equal to alpha of x naught plus n into h. So alpha of x naught is plus n into h is this. So n gets cancelled. Alpha of x naught, alpha of x naught. A is nothing but x naught. So both gets cancelled. We are remained with alpha of b. So that shows alpha of x naught plus h lies in between alpha of x naught and alpha of b. That is, it lies in between alpha of a and alpha of b. So this is a number. Alpha of x naught plus h is a number which lies in between alpha of a and alpha of b. And alpha is a continuous function on closed interval a comma b. So now use the intermediate value theorem. So just recall the intermediate value theorem. So intermediate value theorem says that if f is a continuous real function on some closed interval a comma b, f of a is less than f of b, and sees any intermediate value between f of a and f of b, then there exists a domain point x belong to the open interval a comma b such that f of x is equal to c. So graphically, so suppose f is a continuous function in the closed interval a comma b. So say this is f of a, this is will be the f of b. So it is continuous. So starting from f of a till f of b, we have a continuous flow of images. Now suppose c is any intermediate value between f of a and f of b. So this is f of a, this is f of b. So suppose c is any intermediate value between f of a and f of b, then corresponding to c there is a domain point x such that its image will be nothing but c. So that intermediate value will be image of some domain point in the interval a comma b. So this is what the intermediate value theorem says for any continuous function. Now alpha is a continuous function on closed interval a comma b. So this is an intermediate value between alpha of a and alpha of b. So what it will imply? So there is a point in the closed interval a comma b whose image will be alpha of x naught plus h. So by intermediate value theorem, there exists a point x1 belonging to the closed interval a comma b such that its image alpha of x1 will be alpha of x naught plus h. So the difference alpha of x1 minus alpha of x naught will be h, which we take as delta alpha 1. Next, now consider alpha of x1, which will be obviously less than or equal to alpha of x1 plus h, as h is non-negative. And we can similarly show that this will be less than or equal to alpha of b. So because alpha of x1 is what? It is alpha of x naught plus h. So obviously it is alpha of x naught plus 2 into h. If at all the natural number n which you have considered is greater than or equal to 2, then this value will be less than or equal to alpha of b. So once again, we got a intermediate value between alpha of x1 and alpha of b. Alpha is a continuous function and this is an intermediate value between alpha of x1 and alpha of b. So hence again by using the intermediate value theorem, there exists a point x naught in the interval x1b such that alpha of x naught will be this value. So image of x2 will be this intermediate value. So alpha of x2 minus alpha of x1 will be h, which we take as delta alpha 2. So now up to this step, so we repeated this step twice. So at the first step, we got a point x1 such that delta alpha 1 is h. At the second step, we got x2 and delta alpha to be once again h. And the nature of these points is a is nothing but x naught. X naught is less than or equal to x1. X1 is less than or equal to x2, which is less than or equal to b from the nature. Now repeat the above process. Now apply this step or apply these arguments third time, fourth time like this. So by continuing, by applying this repeatedly or continuing this process, finally what we obtain? We obtain a set of points from A to B, right? So we started with A, that is x naught, and we are ending with B. And in at every time we are getting a point which is in between A and B. So after repeating this process finitely many times, we get a set of points from A to B. X naught is nothing but A, xn is nothing but B. So we get a set of points from A to B such that they are in the increasing form, and in general delta alpha I will be h. Delta alpha I will be h. So what this nothing but, so any set of finitely many points from A to B forms a partition of closed interval A comma B. So continuing the above process, we get a finitely many points from A to B, which will be nothing but a partition with the property that delta alpha I, which we define it to be alpha of xi minus alpha of xi minus 1 is always h. It will be h, which is equal to alpha of b minus alpha of a by n. Here n is any positive integer. So we started with an arbitrary positive integer n, and we obtained a partition P with this property. So for every positive integer n, there is a partition P equals x naught, x1, so on, xn, such that delta alpha I is always equal to alpha of b minus alpha of a by n, that particular n. Okay, so we got a partition now. Now we shall come to the condition. So by Riemann criterion for integrability, to show f is Riemann-Stieltje integrable, so what we have to prove? We have to prove up of alpha minus lp of alpha is less than epsilon. So start with that difference. So up of alpha minus lp of alpha. So what is up of alpha? It is the upper Riemann-Stieltje sum with respect to the partition P and alpha. So it is defined to be summation capital Mi into delta alpha I running from 1 to n minus summation small mi into delta alpha I running from 1 to n, where what is capital Mi? It is the supremum of all f of x as x varies from the ith interval xi minus 1 xi, and small mi is the infimum of all f of x as x varies over the ith interval, which is xi minus 1 xi, right? So as both the summations are running over the same indices, so we can combine the both summations. Summation mi delta alpha I minus small mi delta alpha I. So taking delta alpha I common, it will be capital Mi minus small mi. So what is delta alpha I? So according to our construction of the partition P, so for this partition, delta alpha is always constant, which is alpha of b minus alpha of a by n. So delta alpha I is alpha of b minus alpha of a by n, which is constant, which is independent of the index of the summation. So take it outside. So it will be alpha of b minus alpha of a by n into the summation capital Mi minus small mi, where capital Mi is the supremum, that is least upper bound of all these f of x's, and small mi is the greatest lower bound all of these all f of x's. Okay, next. Now come to the given hypothesis. F is given to be a monotonic function. So F is a monotonic function means F is either monotonically increasing or monotonically decreasing. So what monotonically increasing says? So monotonically increasing function means as the domain points increase, as the value of the domain points increase, correspondingly the function values also increase. So observe here. So if I vary x over the closed interval xi minus 1 xi, so x starts from xi minus 1. So it gradually increase and finally it attains the value xi. So as the value of the domain points increase from xi minus 1 to xi, so the corresponding function values f of xi minus 1, next image up to f of xi. So these will be in the increasing order. So less than or equal to, less than or equal to, less than or equal to, like this, right? So what is least upper bound? So least upper bound of these values will be actually the maximum. So what is the maximum of all these values? So the values starts from f of xi minus 1, and as f is increasing, monotonically increasing function, the function values will gradually increase from f of xi minus 1 up to f of xi. So this will be the maximum value, which will be the largest value. So that will be nothing but the supremum. Similarly, what will be the infimum? Infimum means what? Greatest lower bound. That is the smallest value. So this is the smallest value that function can attain. After this, the function has to increase gradually as f is monotonically increasing. So in this interval from xi minus 1 to xi, as the function f is monotonically increasing, so f of xi minus 1 will be the smallest value, and after that the function value will gradually increase up to f of xi. So the minimum value will be the first value, that is f of xi minus 1. So mi, capital Mi is always f of xi, small mi is always f of xi minus 1. Now we shall substitute it. So summation capital Mi minus small mi, I running from 1 to n. So capital Mi is nothing but f of xi, small mi is nothing but f of xi minus 1. Now we shall expand this summation. Put I is equal to 1. So f of x1 minus f of x0 plus I is equal to 2, f of x2 minus f of x and so on. Put I is equal to n, f of xn minus f of xn minus 1. And you can observe that the terms gets cancelled with opposite sign, and finally you will be remained with f of xn minus f of x0. That is nothing but f of b minus f of a. So that means the summation is nothing but f of b minus f of a. So substitute that value. So therefore up f alpha minus lp f alpha is equal to alpha of b minus alpha of a by n into this summation capital Mi minus small mi. So that is nothing but f of b minus f of a. So we got this, that is up f alpha minus lp f alpha is alpha of b minus alpha of a into f of b minus f of a by n. Observe that. So if I move to the starting point of the proof, so for given epsilon positive, so for any positive integer n, we started to construct a partition. So starting with an arbitrary natural number n, or starting with arbitrary positive integer n, so we constructed a partition P with this property, right? We got a partition P with the desired property. So UPF alpha minus LPF alpha will be equal to alpha of b minus alpha of a into f of b minus f of a by n, where P is the corresponding partition constructed using the natural number n, or the positive integer n. Now increase the value of n gradually. So for every positive integer n, you will get a partition P with this property. So this is the generalized one. So UPF alpha minus LPF alpha is equal to this. So which is true for any positive integer n. So take any positive integer value for n, correspondingly you will get a partition P with this property, right? Now choose n to be sufficiently larger. So for larger value of n, so take n to be crore, n to be million, trillion, like this. So just increase the value of n, or take n to 10 to infinity. So as n becomes larger and larger, so for that positive integer also, for larger value of positive integer n also, there exists a partition P with this property. But as n becomes larger and larger, so observe the right hand side. So as n is in the denominator, as n becomes larger and larger, as the denominator becomes larger and larger, the value on the right hand side becomes smaller and smaller. And we can make that less than epsilon, where epsilon is any arbitrary positive value. So that means the right hand side value can be made as small as we desire, as it contains an arbitrary n number. So as n is arbitrary here, so raising the value of n, as n becomes larger and larger, the right hand side value becomes smaller and smaller, so that we can make this as less than epsilon. So whatever the given epsilon, so corresponding to that, choose a larger n value, so that the right hand side value has to be less than epsilon. So we can do this. So we can illustrate the same thing using Archimedean property also. Now observe that what we have, UP of alpha minus LP of alpha is equal to alpha of B minus alpha of A into F of B minus F of A by n, where n is any positive integer and P is the partition P existed according to the natural number n. Okay, now by Archimedean property, there exists a positive integer n such that n epsilon is greater than this value. So here epsilon is a positive real and this is any real number. This is any real number. So for any positive real x and for any real y, so the Archimedean property says that nx is greater than y. So epsilon is positive real, so n into epsilon is greater than this, or alpha of b minus alpha of b by n into f of b minus f of a will be less than epsilon. So this is the n which has been existed using the Archimedean property. Now for this corresponding positive integer n, so there exists a partition. So as we done earlier, starting with an arbitrary positive integer n, so now consider this positive integer n corresponding to the positive integer capital N. So there exists a partition, say P naught, such that U P naught F alpha minus L P naught F alpha will be alpha of B minus alpha of A by n into F of B minus F of A, so, and which can be made less than epsilon using the Archimedean property. So in this way also we can argue that U P naught F alpha minus L P naught F alpha can be made less than epsilon. So that is, so we made that U P naught F alpha minus L P naught F alpha is less than given epsilon for some partition P. So what that shows, for a given epsilon positive, we found a partition P of alpha, P of the closed interval A comma B such that UP of alpha minus LP of alpha is less than epsilon. So which is the Riemann criterion for any function to be Riemann-Stieltje integrable. So thus we can conclude F is Riemann-Stieltje integrable on the closed interval A comma B. And this is in what case? This is if monotonically increasing function F. If F is monotonically increasing, so we got the desired result. Now the other case. So if F is monotonically decreasing, so F is monotonically decreasing means what? If x1 is less than or equal to x2, f of x1 will be greater than or equal to f of x2. That is, as the domain value of the domain points increase, the function values all actually decrease. So in that case, infimum of all f of x's will be f of xi, and capital Mi will be, that is supremum, that is least upper bound will be f of xi minus 1, because so see here, so in the interval xi minus 1 to xi, in the interval xi minus 1 to xi, so the domain point starts from xi minus 1 and it goes up to xi. So as the domain points increase from xi minus 1 to xi, so the corresponding function values f of xi minus 1, so on like to up to f of xi, so they gradually decrease. So the smallest value will be nothing but the infimum and the largest value will be nothing but the supremum. So f of xi minus 1 will be the supremum, f of xi will be the infimum. So this is the only change between monotonically increasing function and the monotonically decreasing function. So if small mi is f of xi and capital Mi is f of xi minus 1, then the summation will be f of a minus f of b. So just it is the reverse. Now UP of alpha minus LP of alpha will be alpha of b minus alpha of a into f of a minus f of b by n. And now as this is in general for any natural number n, so by choosing n larger and larger, by choosing sufficiently larger n, the right hand side value can be made less than any given positive value. So which shows that for any given epsilon positive, we found a partition P such that UP of alpha minus LP of alpha is less than epsilon. So which holds in the case of monotonically decreasing function also. So thus, in any case, F is either monotonically increasing or F is monotonically decreasing. In general, if F is a monotonic function, then F will be obviously Riemann-Stieltje integrable on the closed interval a comma b by the condition given by the Riemann. So this is the Riemann criterion for any function to be Riemann-Stieltje integrable, and as the function monotonic function satisfies this condition, F will be Riemann-Stieltje integrable on the closed interval a comma b, and this completes the proof. And in this theorem, what we proved that if F is a monotonic function and alpha is any monotonically increasing continuous function on the closed interval a comma b, then F will be Riemann-Stieltje integrable. So this is a very important result. If F is monotonic and alpha is a monotonically increasing continuous function, then the combination of F and alpha will give you a Riemann-Stieltje integrable function. Now, as a corollary for it, so statement, if F is a monotonic function on the closed interval a comma b, and then F is Riemann integrable on closed interval a comma b. So proof, since F is monotonic on the closed interval a comma b, by the above theorem, F will be Riemann-Stieltje integrable for any monotonically increasing continuous function, right? So the previous theorem says that if F is monotonic function, and along with that, if you take any monotonically increasing continuous function, then the combination will be Riemann-Stieltje integrable. That is, F will be Riemann-Stieltje integrable. So F is given to be monotonic function. So along with F, consider any monotonically increasing continuous function alpha. Then by using the above theorem, that is the previous theorem, F is a Riemann-Stieltje integrable function, where alpha is any monotonically increasing continuous function. In particular, in place of alpha, consider the identity function. So define alpha to be alpha of x is equal to x, which is an identity function. So it is monotonically increasing and also continuous. You know that identity function is a continuous function. So it is monotonically increasing continuous function. So F is given to be monotonic function, and we have taken alpha to be the identity function, which is monotonically increasing continuous function. So F will be Riemann-Stieltje integrable on closed interval a comma b by the above theorem. But previously we have observed that whenever you take the monotonically increasing function alpha as the identity function, so Riemann-Stieltje integrability coincides with Riemann integrability. So thus F will be Riemann integrable on the closed interval a comma b. So this completes the corollary. So therefore, in this theorem, we discussed the Riemann-Stieltje integrability of a monotonic function when it is taken with a monotonically increasing continuous function.